This video is going to be on the differentiability of piecewise functions. So when we talk about differentiating piecewise functions, we're talking about the piecewise function as a whole, so including all the parts where the two different pieces or three different pieces come together, and we want to make sure that they all work and that every single point on the domain is differentiable. So the way that we check it is we say if f of x and f prime of x are continuous, and this is specifically for piecewise functions, this is not talking about other functions, then f of x is differentiable. All right, so for the first example, we're going to say, is f of x differentiable? And I'll go ahead and give you a piecewise function. We have the function x squared plus 1 if x is less than or equal to 1, and 2x if x is greater than 1. So the reason that we want to make sure that the original function, that f of x, is continuous is because if it's not defined somewhere, if there's a discontinuity, we know that discontinuities are not differentiable, that there's no derivative there. We have to make sure there's no holes, there's no jumps, there's no asymptotes, because all of those things would not have a slope. So that's why we're checking to see if the function itself is continuous, okay? So we're going to say has to be defined everywhere to have a slope everywhere. So we've got no holes, jump, VA. Can't have any of that stuff if this is going to be differentiable. So to check for continuity, I'm just going to go ahead and plug in 1 to the left side and plug in 1 to the right side. Since we have a parabola for the left side and a straight line for the right side, I'm not worried about the pieces themselves, whether or not those pieces are continuous. I know that a parabola is continuous. I know that a straight line is continuous. I'm concerned with where the two lines come together, where those two curves come together. So 1 plus 1 is 2, 2 times 1 is 2. So now we can conclude that this function is continuous for all real numbers. So that's a good start. Next, we're going to go ahead and find the derivative. So when we talk about if a piecewise function is differentiable, we're not talking about whether or not you can find a slope for each of the pieces. That's not what we're talking about. We want to make sure that there's a slope at every single point on the entire domain. That's what we're checking for. So if you wanted to know the derivative of the left side at at -5, that'd be fine. If you want to know the derivative of the right side at +5, that'd be fine. What we're curious about is whether or not we can say that this piecewise function has a derivative for every single point on its domain. That's what they're asking when they say, is it differentiable? So this is our guess. This is what we think the derivative is, but we have to make sure that it's continuous before we go any further. And the reason we have to make sure it's continuous is we have to make sure that all of our slopes are matching up. So we're going to check the left-hand slope at 1 and the right-hand slope at 1 and make sure that those slopes match. Because if they don't match, then we have something like a sharp corner going on, and we know that sharp corners are not differentiable. It means the original function had a sharp corner, and so they wouldn't match. All right, so 2 times 1 equals 2. There's my left side, there's my right side. And those do match, which means that this piecewise function was differentiable on -∞, infinity. So for the original domain with the problem, every single point has a derivative or has an instantaneous rate of change. Now, one thing that students are often maybe rusty on or have never learned to do is how to graph a piecewise function using their graphing calculator. So I believe if you have a color calculator, those ones I think have a special function where you can like actually type in the piecewise function. But if you don't have that, you can still graph it. So I'm going to type in x squared plus 1. That's the first piece. And now to type in that limited domain of x is less than or equal to 1, I hit the divide button to put a slash there. And then I put a parenthesis, and now I'm going to type x is less than or equal to 1. So I type the x. To get the less than or equal to, I hit second math. And then that's where all my inequality symbols are. So less than or equal to 1. Now I've got 2x. X is greater than 1. Second math, greater than 1. And you can see when you graph it that those two pieces did connect. They were continuous. And now I can go ahead and I can even graph the derivative. And I get 2x if x is less than or equal to 1. And I get 2 if x is greater than 1. And so I can see that the derivative is continuous as well. So if you had a graphing calculator, you could do that problem real quick and see if they're continuous or if it's differentiable. You wouldn't even have to graph the derivative to see if it's differentiable. You could probably do it by sight for the most part. But a lot of times you're not going to have a calculator, so this is the proper way to do it by hand. Okay, so here is one more example. Is f of x differentiable? Again, that's the question that we're asking. Actually, I should have written my final answer. Yes. That's what the answer was. All right. So is f of x differentiable? The answer is yes. So I'm going to go ahead and write this problem. X squared plus 2, x plus 2. If x is less than or equal to 1, if x is greater than 1. So first we check for continuity. 1 squared plus 2 needs to equal 1 plus 2. So 3 equals 3. That's a good sign. We know that this graph is continuous for all real numbers. Now we need to check the derivative to see if we can differentiate all those points that we have. So check for this continuity. So this one we would say is not differentiable at x equals 1. So there's an issue. We can find the derivative everywhere else, but we cannot find the derivative at 1. So f of x is not differentiable at x equals 1. So you can find the derivative everywhere else, but 1 is a problem. All right, let's go ahead and do another example. I'm going to stop writing is it differentiable, but you know that that's the question that we're asking. So 3x plus 2, x to the third plus 4, x is less than or equal to 1, x is greater than 1. So we've got 3 times 1 plus 2, 1 to the third plus 4, 5 equals 5, that is true, so this is continuous for all real numbers. And then let's go ahead and find the derivative of each piece. So 3 equals 3 times 1 squared. So this is differentiable for all real numbers. And so we can say, yep, it was differentiable. Now, when you're doing problems, if they ask you about the differentiability of a piecewise function, they're not looking for the final yes or no answer, even though that's what I'm putting a box around. these are the two things that they're looking for. So if you are using calculus to show the differentiability of a piecewise function, these are the two statements that are kind of the key to making your case. All right, one last example. We're going to kind of kill this dead so that you're like, yeah, that's easy, Miss Rice, stop this video. So again, 2 times 1 squared plus 1 minus 1 should equal 5 times 1 minus 3. So that's 2, that's 2. So we've got that this function is continuous. Now we'll go ahead and check the derivative. And if I plug in 1, I get 5 equals 5, so it's also differentiable. So if they took it a step further and they said, go ahead and tell us what the derivative is at the point of interest. The point of interest was 1, an x-coordinate of 1. That's what we were interested in. So if they want us to find the value of the derivative there, then we would just be saying, okay, if I plug 1 in, I get 5. So here, if I wanted to know, I'd say f prime of 1 is 5. And of course, you could use your derivative to find other values too. If you wanted to find f prime of 0, 0 is less than 1, so you'd be using the first piece, and your derivative there would be 1. So it's possible to find the derivative using a piecewise function at a different point. It's just less interesting. So when we talk about finding derivatives with piecewise functions, we want to talk about like what's the hardest part of it, and the hardest part is that point where the two pieces come together.